Okay, hello. Is this actually on this time? Hopefully. I see people saying stuff in the chat. Okay, great. Great. Randall says it is on. I am glad it is on. Happy Friday everybody. Uh yeah, it's Friday. I feel like this is the first stream I've done this year. Or I feel like I haven't streamed at all since last year. It's been a year. Oh man, I messed up this joke. Anyway, hello everybody. Thank you all. Thank you all for coming today. Welcome to my stream. We are going to do some stuff today. I will just start the keynotes now. Let's do it. Oh, let's actually hit play on the keynote. I I tried to stream last week and just completely messed it up, so I'm glad it is happening this week. Hello everybody. Welcome to the Cool Stuff live stream. This week I'm going to talk about TenderJIT. I'm going to talk about ARM64, IRs. We're going to talk about SSA form as well as register allocation. And as always, if you have questions about anything, the stuff I'm talking about today, like put it in the chat. Feel free to ask. I am happy to talk about any of this stuff. So first, I want to say hi, YouTubers. It's been a while since I've done any live streaming, and I would appreciate it if you all make sure to subscribe, and smash that notification button. um, I guess I haven't streamed since September last year, and I've been like, I don't know, I've just been doing other stuff. I started making clickbait thumbnails, so I want to share some of my clickbait thumbnails with you. I made this one, like, how could YJIT do this? And and also rake TV drop in production. Ah! Um, I so last week I tried to do a live stream, and of course I shut off all of my notifications because I don't want the notifications coming up while I'm doing a live stream. And it turns out like I didn't stream anything at all. I don't know. I have no idea what happened. It just didn't go. And so I basically was talking to my computer for about an hour by myself, and I felt very dumb about it. But then Inky Voxel made this this clickbait thumbnail, and it cracked me up. I thought it was very funny. Um, so I've also been working on Initial V. So I'm going to talk about this project a little. I've been working on this project for quite a while, and I will do a live stream about it one of these days. When I get it done, I will do a live stream and talk about it. But what it is a BMW shift controller thing. But I've designed a PCB that you stick into the back of it, and it turns it into a Bluetooth keyboard. And I made it so it's supposed to be a Vim stick shift basically. So like you're in Vim and you put this into neutral mode, and it puts Vim into normal mode. Or if you hit P for park, it'll hit escape and save the file for you and stuff. So I'm working on the hardware is basically done. I'm working on printing a case for it so it looks a little bit nicer, and then once that's done, I'll probably I'll do a live stream about it. But honestly, the reason I haven't done any streaming in a while is basically just burnout. I put a lot of work into prepping for these live streams. I didn't realize how much work it would actually be. So I was trying to do it like every other week, and it turns out it's pretty difficult to make a presentation about Ruby internals and hard stuff every other week. So I decided to quit doing it for a while. But I think this year I'll try to do it a little bit more sustainably, maybe like once a month or so. But yeah, I've also since last week. So, so I basically had an hour to practice. I practiced this whole live stream last week because I didn't actually stream it. And while I was streaming, I found I was saying saying these like acronyms and stuff that are in the Ruby source code, and I keep explaining them, and of course I'll still explain them on the stream, but I realize that like there's a ton of different just like jargon and like I don't know, acronyms and stuff in Ruby's source code that if you don't know, it's really hard to understand. Like I think it's hard to understand what's going on. So I started a glossary for Ruby internals. I probably shouldn't have named the repo Ruby glossary because it's really Ruby internals glossary. So like it's really targeted at folks who want to read Ruby internals and understand what's going on there. So if you have any questions, like uh, file an issue. Like if there is a term you're reading the Ruby source code and there's some term you don't understand, just like go ahead and file an issue. Or if you see one that you do understand, send a pull request. I mean, yeah. So if we come across any today, then I will add them as well. Today we're going to talk about TenderJIT. Like I want to talk about TenderJIT this week, so we're going to do that. Next month, I was thinking possibly application profiling. Something I'm interested in doing is like one of the gems I work on is StackProf, and I think it would be cool to do a live stream about StackProf, how to use it, how to like I don't know, tune your application and find bottlenecks and stuff. I was hoping like maybe I can set up a Mastodon instance locally and try profiling a Mastodon instance, since I know that's a hot topic these days. But anyway, if there's anything else that you want to talk about besides Ruby internals and compiler stuff, like please toot at me. I am tenderlove at mastodon.social, or just send me an email and I can do it too. So let's talk about TenderJIT today. So for those of you that don't know, TenderJIT is a pure Ruby JIT compiler for Ruby. And I was talking to one of my coworkers, and he said to me like, "Oh, well, you know, I've seen you talk about TenderJIT on the live stream, but it doesn't look like you're actually writing Ruby. It looks like you're writing assembly in Ruby." And I was taken aback because it's unfortunately very, very true. However, if you look at the YJIT internals, you'll notice that YJIT is just writing assembly in Rust. So, like, hey, you want to write assembly in Ruby or assembly in Rust? I don't know. You pick one of those. Anyway, I want to work on. I kind of put down TenderJIT for a little while, and the reason was because I got a Mac and it's an M1, and TenderJIT is x86. It only works on x86 machines, so I didn't want to I don't like firing up Rosetta and messing with all that stuff. So I don't know, kind of quit working on it. So what I want to do today is we're gonna start working on an ARM64 backend for TenderJIT. I also want to overhaul the IR in TenderJIT. It didn't have a very good IR. I thought it was kind of interesting. It has kind of a DSL that looks like Ruby, but it's not. I'm gonna do an intermediate representation, a little bit better one, I think, and then we'll take that IR and convert it into translate that into ARM64 code. We're also going to take a look at some Ruby 3.2 features, and by features I mean a feature. We are going to look at a Ruby 3.2 feature, not many features, just one. I don't know why I put an S in here. So let's talk about Ruby 3.2 features. One of the features I want to take advantage of in TenderJIT is something implemented by Kokobun. Kokobun is the original author of MJIT. He added a thing to Ruby 3.2, which is a kind of a BYOJ, or bring your own JIT compiler framework into Ruby 3.2. So he made it possible, if you look at the original TenderJIT code, it works with Ruby 3.1, but the stuff that I had to do to plug into the JIT compiler in Ruby 3.1 is really, really awful. It should be illegal, the hacks that I had to write for this thing. And fortunately, Kokobun was kind enough to add hook points in MJIT such that we can actually hook into the compiler and say hey, I want to give you my own compiler. I want you to run my compiler instead of the other one. Here's an example. Here's an example of it. All you have to do is you have to monkey patch. So you just monkey patch mjit. You define a compile method, and you make sure you have to start Ruby with mjit pause, and then inside your code you define your compiler, and then you say, hey, mjit resume, and after it resumes, then it'll automatically call into your compiler. So you can do whatever you want to. Like, you do whatever you want to in your compiler. So in this example here, you can see like I defined a compile method. The compile method just prints hi mom, and then exits, like it hard exits the program. And if we run this with mjit, you can see like it does call into my compiler. So what we do is, to actually implement this, I know the code is very small here. Don't worry, we're gonna read it. Hello, Colin. Thank you for coming. I'm glad I'm actually live this time. It's okay that you're late. I am a week late. Yes, I'm live finally. I'm so glad to not be just talking to myself. All right, so this is, we're gonna look at this code. You don't need to read it. Don't read it too closely, because I know it's small. We'll look at it in Vim. But what you have to do is the interface for this bring your own JIT compilers is just like, you get the instruction sequence that you need to compile. And the thing that you have to return is you have to return a function pointer address, or you have to return an address back to mjit, and that's the address that mjit is going to execute. So it's going to think of that as the function pointer. So if we define our own function pointer, we can do that. Let's zoom in on this code a little bit. This is the code from the previous slide. All it does is writes out some assembly code in ARM64. It defines some ARM64 code that pops the current Ruby frame. So we're gonna say, like, whatever you get called with, we're gonna pop that frame, and then we're just gonna return the value 5, which is like not, I mean, whatever. It just returns 5. We're demonstrating that the compiler works. So you assemble some stuff, and then the thing that you need to return is you need to return the address that you want executed. And in this case, it's a JIT buffer, so it's some executable memory. But there is some problem with this code. Like, very clearly, this code is ARM64 specific, so it will not run on an x86 machine, and that's not great. So we should probably fix that. And the way we fix that is by using an intermediate representation. So I'm working on an intermediate representation for this new version of TenderJIT. We're going to look at it today. All an intermediate representation is it's kind of like machine code for an abstract machine. So we're going to define this like pretty low level language. It's like a pretty low level language, but it's abstract. It's not targeting one particular processor. And then we'll take that IR and convert it into the machine code for the particular processor. So that way, like, when we get it working with ARM64, we can switch out the translator to translate it to x86, and then we'll have a cross-platform support on TenderJIT. I'm also using SSA form, or static single assignment form, and I'll explain what that is. I'll give like a brief explanation of what that is, but there's a really great YouTube video from I think the guy's name is Vivek. He just like reads papers, CS papers on YouTube, and explains them. They're really, really great videos. I put a link in the description to his reading about the SSA form paper, and it's very easy to understand. So I definitely recommend check out his channel and watch his videos. They're good. I am a fan. Anyway, SSA form, oops, I'm going to go forward. So SSA form is a low-level language. It's kind of a low-level language, and in my case, I'm going to use 3 parameters at most. So I guess you could have like 4 parameters, but I'm going to use 3. And the idea behind SSA is that we only ever assign to a variable once. So we only assign to variables once in SSA form. So kind of our triples will look kind of like this. So let's say we have some Ruby code that's like A equals 2, B equals 3. It's that code, the code that's on top there. We'll translate it into these triples that are like, okay, write 2 to A, write 3 to B, and then add A and B and put the return result in C. So it's at most 3 parameters. Like those first two only have 2 parameters, but you could actually think of those writes as an addition where you're just adding like 0 to a value, right? But this is kind of what it is. Variables are, I think I said this, variables are only defined once. And the reason for that is we can figure out, like, we can learn a lot of stuff if we only assign to a variable once. Like, we can understand how long a variable needs to stick around. So let's say, for example, we have this code here. We assign 2 to A, 3 to B, and then we do some math on this stuff. And you can see, like, kind of near the bottom, we redefine B. So we write over B. So it's kind of like, how do you write a program that analyzes this code and figures out how long B is supposed to be assigned to 3? Like, how long does that need to live? And you can do that, but it's just kind of hard. But what you could do is, if we convert this code into SSA form where we only assign to variables once, then it becomes pretty obvious how long B needs to last. So we'll rewrite it in SSA form. And all you need to do is you just like create a new variable. That's all you do. So you just basically pretend you have an infinite number of variables, and then just like, if you need to write a new variable, just do a new one. So here you can see like, well, B only has to live until we do C equals A plus B. After we do that assignment there, like, we don't actually need the value of B anymore. So it's okay for us to forget about that particular value. There's other optimizations you can do with SSA form, but I'm not gonna go into them. Like, definitely watch Vivek's stream. Also, I think there's some books about SSA form as well that'll go over other optimizations you can do with this form. But this is what we're going to be using in TenderJIT. So here's an example of the Ruby code I've been writing. Like, this is the kind of SSA form that I started doing. So here we're defining a function that takes 2 parameters, adds the 2 parameters, and then returns the result. So here we'll just take A is parameter 0, B is parameter 1, we add the 2 and then return it. So that's kind of what it looks like. So why do we care about variable use? In my particular case, the reason I care about how long a variable is used is because I need to understand, I need to allocate registers to hold those values in. So our machines operate on registers, so we have to load a value into a register in order for to tell the CPU to do stuff with it. But the problem is that registers are finite. We only have a certain number of registers available to us in the CPU. So we have to have some sort of scheme to figure out like how we put values into registers and what values we put into registers. So SSA form allows us to easily evaluate the lifetime of variables, so we can understand how long we need to occupy any particular register. So I've written a register allocator, and the register allocator is just an object that tries to figure this out. Like, it allocates registers to real registers. So it coordinates all of that register allocation. The one that I've written in TenderJIT so far, we'll take a look at the code after I'm done with the slides here. It's a linear scanning register allocator. So all it does is it scans the code down and says like, hey, how long is this thing going to be used? Sage is asking, please tell me if you ever do a talk about things you'd like to. Oh, you'll title it the Aaron of Grievant. Oh boy, yes, I will absolutely do that. So the register allocator I wrote is a linear scanning register allocator. It just looks at each variable and it says like, okay, for each line or each instruction, like how long is this thing used? Because you can think of the instructions, our SSA form instructions are just stored in an array. So all we have to do is we have to say like, well, what is the last index in the array where this thing is used? and then we know the lifespan of it. What is the first index and the last index? And then we know how long the thing has to occupy a register. So here we'll walk through the actual like evaluation of it. So here we say like, well, okay, we need to assign A to a register. We'll keep kind of a queue of registers that we can push and pop from, or like to get the register we need. Here we say, well, A needs a register. X0 was free, so let's just put the value in X0. So we're good here. We know we can put it there when we generate machine code for this. So we'll do the same thing for B. B needs to be in a register. We know that A doesn't die until later on. Like we can't lose it. So X0 is occupied. X1 is not occupied, so we just stick B into X1. Now we have kind of a problem here. Like we only have 2 registers in my imaginary machine here, X0 and X1. Here on the third line, we're doing an assignment. We're saying like C equals A plus B. So we need a place to store C. I guess my animations were a little too quick here. But what we do is we say, well, okay, I'm gonna move this over here. Yeah, there we go. So now it looks like it's like I'm more looking at the screen. Nice. All right. So we have to have a place to store C, and we can see here that like B is no longer used after this assignment. So we can free up that register. So we say like before we calculate the register that C needs to go in, we give the operands for that instruction an opportunity to say like, hey, are you done? So if they are done, then that way we can be like, hey, let's reuse that one register. So in this case, we free up X1, and because B is no longer used, and then we store C into that value. So we know at this line C is going to go into the X1 register. So I got to highlight keynote. There we go. So then we move on to the next one. We have B1 here. B1 equals A plus C. We go through the same process. We say like, hey, A, can you free yourself? And A is not used anymore, so we know that X0 is free. And we store B1 in X0. And then down here on D, it doesn't really matter because the program is ending. B1 and C are not used anymore. So we'll just say, hey, we're going to store D into X0. So through this like process, we can check the lifespan of each variable. And I actually kind of think of these variables not as variables, but as free registers or like imaginary registers. So you can imagine like we're pretending that we have a machine that has an infinite number of registers, and then we're checking how long each of these like virtual registers lasts, and then assigning them. The register allocator is assigning actual physical registers. All right. The other nice thing about SSA is we can do easy peephole optimizations, which we might do in this stream. I'm not sure. We'll try to get to it. And also we can target any machine, x86 or ARM, as I already said that. Here's the code for the register allocator, which is probably too small to read, but we're going to look at it in Vim in a very large font, so don't worry. Just a quick refresher before we start hacking on TenderJIT. YARV is a stack machine, so it operates on a stack. So for example, we have this function here, foo, that calculates 2 plus 3. When we generate YARV machine code, it's generating bytecode that operates on a stack. So in this case, we'll say like, hey, we push 2, then we push 3. Randall is asking, Randall, I'll answer your question in a second after I get through this animation. And I'm going to move, can I just do keynote only? Let's do that. Hey, there we go. Okay. So we push 3 on the stack. We add the 2. The add instruction pops the 2 off of the stack and then pushes the value on. And then the leave instruction will return the value 5 from that function. So Randall is asking, how different is ARM64 architecture from x86? I would say the answer is pretty different. It's pretty different. One really nice thing about ARM64 is that ARM64 doesn't really operate on memory. So there are x86 instructions. Here's a really simple example. Let's say you have a value in memory and you want to increment the number, and it's stored somewhere in memory. Well, there is an instruction on x86 where you can say like, hey, I would like you to increment this value, but the value is stored somewhere in memory. Okay. And it'll do that. It'll go increment the value and keep it stored in memory. On ARM64, we can't do that. We have to load and then store it. So we would say, hey, that would take 3 instructions. We would have to say, hey, I need you to load a value from this place in memory, increment the value while it's in a register, and then store that register back where it came from in memory. So x86 is able to perform a lot of operations on memory locations. ARM can't do that, but I actually think it makes the code a lot simpler with ARM. Another cool thing that I like about ARM64 is that all of the instructions are 32 bits wide, so it's very easy to write an assembler for it, but that's not the case on x86. x86 instructions are variable width, so like the width of the instruction depends on what the instruction is and also what the operands are. So writing an assembler for x86 is much harder. All right. So back to our stack machine. So YARV is a stack machine. YARV is a stack machine, and our job here is we want to take this stack machine and convert it into a register machine, because the real machine is actually a register machine. It's not a stack machine. So we need to take these instructions and convert them into ARM64 code. So here is an example of ARM64 code that does exactly the same thing as our YARV instructions. We say, hey, let's put the value 2 into x0, then let's put the value 3 into x1, and then we'll add x0 and x1, and we'll store the result value into x0. So x0 and x1 get added together, we store the result, we store the value, and then finally we return from the function. So our high-level goal is essentially to do 2 or 3 passes on the YARV bytecode. Our first pass, we're going to get YARV bytecode. We're going to take that YARV bytecode, iterate over it, convert it into an IR in SSA form, and then finally we'll output machine code. And possibly in the middle here, we may optimize here. So if we have time, we'll do it. There's some I would like to do, but if we don't have time, then we won't do it. So we're going to convert some instructions, hack on SSA representation. Also, we'll look at the mjit hooks, so you can BYOJ or develop your own JIT kit. Yeah. So let's. Oh boy, I forgot that I can come back on. I'm back on the screen. Yay! All right, so we're gonna do all this stuff. Let's go to the terminal. Desktop with me. Yay. Okay, I switched sides, so it's like, hey, I'm looking at the thing. All right. All right. So this here, I'll bump up the font a little bit bigger. I'll make sure everybody can read this. There we go. If the font's too small, let me know and I'll change it around. Okay, so this is the example that I showed in the slides where we're hooking into the mjit, like the mjit compiler. I've pulled in the JIT buffer gem, which just gives us an interface to a JIT buffer that we can put our native code into, and then I added my ARM64 assembler here as well. So all we do is we hook into, we monkey patch the compile method onto mjit here, and then when mjit executes, it'll see that, hey, there's a custom version of compile, and it'll actually pass in the instruction sequence that it wants it to compile. So here, all I'm doing is just assembling some x80 or ARM64 code that just pops our frame. It puts the value 5 into the x0 register and then returns. Then we write that out to the JIT buffer here, and then we return the address back to mjit. So you can see here the method foo normally returns 1, but the code that we're executing here is going to return, it's going to make a return 5 here. So if we run it, let's run it. Ruby, actually, let's check my version. Yeah, it's not going to work with that. Ruby mjit pause. So this pause basically says oh, let's bump this font up too. bump that font up. You know what I should do? I should also get rid of this thing. I'm not going to figure that out now, but in future streams, I'm going to get rid of this so that we can have more room on the screen. Okay. Put this here. All right. So we'll say like, hey, we're going to pause, and this means like, hey MJIT, I want you to be enabled, but I don't want you to run anything right now. So this turns on MJIT, but it says like, don't do anything. Then this here, this MJIT call threshold, I think there's a bug, but I'm not 100% sure. Because you can say like, hey, I want you to, on the third time a method is invoked. Oh, let's do this. The third time a method is invoked, I want you to execute the JIT compiler. So then we got our mjit basic here. All right, so we'll run this. And you can see like, oh yeah, we got one, and then we got 5, which is obviously wrong. But you can see that like our JIT compiler actually ran, and we got some machine code to run out of this thing, so it works. All right, so the next thing I want to look at, like this was from the slides. Let's also take a look at the register allocator I wrote. As I mentioned, in my slides, that the register allocator I wrote is not good. Like it's not very good, and we'll look at it, and I'll tell you why. I'll tell you why it's not good when we look at it. Where did I put that thing? ARM64 register allocator. Here we go. So this is the register allocator, and the interface to it just has 3 methods. The 3 methods are like given, here, let's do this. Right here, given a virtual register, I want you to ensure that this virtual register has a physical register that I can use. So if the virtual register already has a physical register associated with it, just return that physical register. Now, here I added kind of a hack. I guess it's kind of a hack. We say like, if this is a parameter, then I need you to get the virtual register from a specific list. And the reason we're doing this is because on ARM64, you pass parameters via specific registers. So there's what they call a calling convention. And on ARM64, the first parameter is always going to be in the X0 register. And then the second parameter will be in the X1 register, et cetera, but it only supports the first 8 registers. So if it's a parameter, then we know that it has to come from one of these, like this pool of parameter registers, so we're going to associate it with that. Otherwise, if it's not a parameter, we're going to call the alloc method with a virtual register. Now the alloc method, all it's going to do is it's going to look at our free list. We have a free list of, up here we have a free list of registers that we're free to use. We're okay to use these. And I've defined that free list as just these 2, like these 2. We're only going to deal with 2 registers. So you're free to use either X9 or X10. Those are the 2 you can use. So down here we say like, hey, I'm going to pop off the free list. Like if there's anything in the free list, give me that register. And if I got something from the free list, then we'll assign that as our physical register. If the free list was completely full, then it means that all the registers are currently occupied, and we can't allocate a register. Now here's one of the weaknesses of the register allocator I wrote, which is if we've run out of registers, typically what normal compilers will do is they'll spill the register to memory, like probably the stack, and what that means is we're going to store the value in the stack. We're going to store it in memory somewhere. We're not going to store it in a register. We have to store it somewhere else. In my case, I'm just raising an exception. So if we ran out of registers, like it's just going to blow up. So our goal here with TenderJIT is that we will never do this. Like it just means that we're not allowed to use more than 2 registers at the same time, which we can figure out how to do. And honestly, like we could add a 3rd here too. We'll make it 50% better by adding a TenderJIT, now 50% better. One more register. All right. So finally, the 3rd method here, like the third method is just freeing it. So we say like, hey, we're done with this physical register. Please get rid of it. And it just pushes it back onto the free list. That's it. So that's how a register allocator work. Sage says, it's just a parameter, Aaron. What could it cost? 10 registers? All right. So we have here's our register allocator. Let's also take a look at the IR, because I think that's kind of interesting. So here is the IR, like this is the IR object, and maybe we should look at let's look at some code that actually uses the IR object first. Maybe that might be a little bit more instructive. I tried to prepare some stuff in advance here. Yeah, okay, this is probably good enough. I'll try to explain it. So we create a new IR object. Now, oh boy, yeah, this is where, when I was practicing this last week, this is where I ran into all these acronyms, and I was like, oh man, this is like not easy. So let's look at, we're gonna zoom back a little bit. We're gonna look at how mjit works in CRuby. So we'll do lcd vm.c. So in vm.c, we keep track, like this JIT exec function keeps track of the number of times a method has been called. So it just increments this total method calls thingy here. And that's how we know, when it's time to start compiling stuff, because we know that that's there. So we have branches in here for YJIT and mjit. YJIT, yes, meaningful variable naming. Yes, exactly. So YJIT is kind of privileged, I would say, in that it's hooking straight into CRuby, whereas my TenderJIT cannot do this. But that's why we have these branches in here. You see, like if YJIT is enabled, we'll do some stuff. Oh. Yes, Benoit was saying, why? Who needs filling? Yes, that was another thing I forgot to mention, is that ARM64, I think there's 32 registers. I don't think you can use all of them. I think you can't. There's 2 of them that you can't use, but it has way more registers than x86. So that's cool. It's kind of a trade-off. Like on x86, you have instructions that will manipulate memory. You don't have those on ARM64, but you have way more registers to work with. So you can do okay. All right, so if YJIT is enabled, YJIT will try to compile it. This is a specific one for YJIT. I think that this could be implemented in terms of mjit, like an mjit plugin. Down here is the mjit plugin one. Like if mjit is enabled, then we'll go do it. So here in mjit iseek, we're not going to step through all this code. It's very complicated. But what this will do is this decides if it should call out to the custom JIT, or if it should be if it should call into mjit itself. Anyway, the result of either of these 2 cases is that we end up with a function pointer. So this is the function pointer here. We end up with some kind of function. So the responsibility of this function or this function is that we need to figure out a function pointer that we're going to call into. So that's how we enter machine code. Then down here, let's scroll up a little bit. Use my arrows. Right here, we actually call that function pointer. So this function pointer gets called, and you'll see here we're past 2 parameters. We're past the EC, which if you look at my glossary stands for execution context. And we're also past the CFP. So CFP stands for control frame pointer. So any function that we generate is going to take 2 parameters, EC and CFP. Execution context and control frame pointer. So you see that here on my JIT side, our first parameter is the EC, so that's where that came from, and our second parameter is the CFP. Now, I wanted to do something special here, which is that I know that we're going to use the SP quite frequently, which is the stack pointer. As I said, we were working YARV is a stack-based virtual machine, so we deal with a stack a lot. And I know that means I know we're going to be reading and writing to the stack frequently. The other thing is the EP. I know we're going to be dealing with the EP as well, or the environment pointer. And what the environment pointer is for is any local variables. So we're going to read and write local variables into the environment pointer. So stack pointer is our stack manipulation. EP is going to be our locals. EPA, yes. Execution context memory. Yes, indeed. All right, so I wanted to make these another I don't know, weak point of the back to weak points about the register allocator that I've written is that it's a very simple linear scanning register allocator, and what that means is it can't understand loops. So let's give a really quick example is if we had a loop. Oh, what's this? This might be important. I'm going to comment it out. Or end. All right. So if you have a loop that's like, I don't know, whatever, any kind of loop. Let's do like while I is less than 100, I minus, and then we have like, oh, I don't know. I can't even think of an example. Like maybe we access some local variable here. I don't know, x plus 2, x plus 1, something like this. Now, typically when you're implementing a loop like that, the machine code is gonna have to jump from this end back up to this while. And the problem is we have variables inside of this while loop that are important and they need to stay alive. And with a linear scanning, like our linear scanning register allocator, if it sees something like this, it's going to assume that some of these died. Like at the end of this end loop down here, it's going to be like, oh, I is dead. When in fact it's not dead. We're reusing it a bunch of times inside this while loop. So this is like the two caveats I'm putting into TenderJIT's IR. One, you can't use more than 2 registers, and 2, don't write any loops. So that's our 2 caveats for now. So I'm not saying that this is not a great register allocator, but it works. All right. So here we have permanent, I've decided to call these like permanent registers. So because as I was saying, this thing can't tell when stuff is going to be like, if we have loops, or different blocks, the register allocator won't know if something is going to be used for a long time. So what I did is I said okay, we're going to make these permanent, and this is requesting that the register allocator never deallocate these. So let's actually look at this IR thing. So we have IR here. Here's another IR example. So we're saying, hey, I want you to do a load IR. I would like you to load, and I would like you to load from the CFP register. And I would like you to load the offset of the SP. So given the SP inside of the control frame, go ahead and load that, and then I want you to write that into the SP location. And we have exactly the same thing down here, except instead of SP, we're doing the EP here. Okay. So let's look at let's actually look at that register or the IR for a second. So here's the code. Here's the code for it. It has a bunch of different methods for stuff we can do. Like we can say, hey, I'm dealing with a parameter at value 0, like the 0th parameter, or hey, I've got an integer. But more interestingly is let's say we have a write, we have an add. Our add takes 2 arguments. So all of these IR methods, they take 2 inputs. So this is going to be a virtual register here, another virtual register here, and they actually return a virtual register. So in the write case, we're going to return the same register that we, like this one. But here we have an add. So we're going to take 2 inputs from the add, arg1 and arg2. And if we go look at the push method, what the push method does is it says, okay, hey, virtual register A, you are used at this instruction. We're just keeping a list of instructions. We're saying, hey, A, you were last used at this index of the instruction. B, you were also last used at the index of this particular index. And then we're going to say, hey, let's create a new instruction with A and B. Those are our two input virtual registers. And then we've allocated an output virtual register here. So we say, hey, I want you to like stick that output virtual register in right here. So we've defaulted it here to the third one as an output register. And then we return that virtual register here, right? So this is why we can write like ir.add a, B, so C is here, so the result of C is, the result of this add is going to be in that virtual register, and then we can say like D equals, I don't know, ir.add C, comma, ir.u imm23, something like that. So we just take these outputs, these virtual register outputs, and we use them as inputs to following instructions. And when we're pushing them onto that list, we can keep track of when they were last used. So we can keep track of the maximum location in the instruction array where it was used, and that's how we can decide whether or not we should get rid of them. So let's go look at the assembler now. Lib TenderJIT ARM64. Let's look at our code generator. All our code generator does is it just loops over that list of instructions, and it says like, okay, here, give me your list of instructions, IR. This is the instruction, and then this is the index. We have 3 virtual registers. As I said, our SSA form is only dealing with 3 parameters. So we have 3 things. We have virtual VR1. These are our inputs, and then this is our output. And then we say, hey, I'm going to call ensure on VR1. And this will give me back a physical register to read from. And then I'm going to call ensure on VR2, and this gives me a second physical register to deal with. Then we say, hey, I'm going to give these two physical registers an opportunity to free themselves. So I'll say, hey, go ahead and free yourself if you can. If you're not used after this, go ahead and free. And then finally we say, hey, okay, for our output one, we're going to ensure a register here. We're going to ask for a physical register for our third one. And this is how we're able to say, like, in the case of, like, you know, if we do, what was that example? C equals ir.add a comma b. If we know that b is never used later, then C can be written into the location of B. So it's okay to use the output parameters or the input parameters as an output, as long as we give them the opportunity to put themselves back into the work list. Then finally down here we try and free the output one as well. We give the output one an opportunity to free itself. And remember, the freeing just means putting yourself back into that list or that queue. Finally, we say, hey, I'm going to go ahead and call send on whatever the operation is, and then I'm going to pass you your 3 registers, your inputs, and then your output right here. And all send does is we just have the implementation of all these things. So for example here, JLE, this is our IR call for a jump if less than or equal to. There's no like direct JLE instruction in ARM64. We have to do a comparison first, and then we say, hey, I'm going to branch if less than or equal to, and we're going to branch to this particular destination. And then negative, so in IR, our IR has a negative command, and that maps 1-to-1 with an ARM64 negative. Same with bitwise and then an add. Return is kind of interesting. We say, like, when we return a value in ARM64, if we return, the return value has to be placed in the X0 register. So here it says, like, well, if our output register is not equal to X0, then we're going to have to go ahead and move it into, like, copy it into X0, and then we'll go ahead and return from the function. And then down here we got stores and loads, and then finally writes. This one is for debugging. We can like set a break. we can set a breakpoint in our code and say like, hey, I want the debugger to break here. Not unconditional jumps, and then we got labels too. So kind of a whirlwind tour of our IR. Let's look at, oh boy, I only have 10 minutes. I hope folks are enjoying this. If there's any questions, like please ask. Let's see what we have in here. MJIT basic, MJIT hook. Did we look at this? Yeah. So this iSeek object that MJIT gives us is pretty interesting. It's got a lot of data on it, so we can actually get like the method name that we're compiling on the body of the instruction sequence. Randall is asking, do we have tests for this code? I feel like that is a trick question. I need to put up the this is a trap meme right here. No, there are no tests. I mean, maybe I wrote some tests. Like there's tests for, actually no, that's not true. We do have tests. Let's look at the tests. Test, intermediate test. We'll look at the test for the IR. Actually, I should have, thank you for bringing that up. I should have done this. This might have been more instructive. So here we have like, right here is our IR. We take 0, 1, we add them together and we return it. And the way that I tested this is I assembled it and converted it into machine code, and then actually called into the machine code and made sure it returned the right value. Man, let's look at so we have, here's all of them. Like these are tests for all of our IR. It was a Thank you, Steve. Yes, it was a test. TechnoSelf is asking, what is this arrow technology? It is an app called ScreenBrush, which I will put in the description, but it is not there now. I have like a IR test. Yeah, let's look at this. What did I leave this? Let's look at the state that I left this in. Let's do this. We'll do some of the ones from the test. So we have param A, B, A plus B, return. Why is it not? There we go. There's our highlighting. Okay, so we'll assemble it. We'll write it to a JIT buffer, and then let's not execute it. So this is our same thing. We had like, right here is we're creating a function that has two parameters, A and B. They add the two together, they return the value. We're creating a register allocator and a code generator. We ask it to be assembled, and then after it's assembled this is actually ARM64 assembly. Once it's assembled, we write it out to the JIT buffer. And down here, let me get this, let me get out of the way here. There we go. Oh, thank you. ZT in Vim, you hit ZT, it'll take it to the top. So we'll write it out to the buffer, and here we're not going to execute it, we're just going to disassemble it. So let's do that. So this is our, remember, like, this is our code here. So this is the code that we're actually making. If we run this, let's do IR test. Can we just run it? Oh boy. Do that maybe. No. Return U. Yeah, we need to return. Let's return T. It'd be cool if we did that. So we see here, like, here is our IR, T equals A plus B, and then here is the ARM assembly code that we wrote. So it's kind of weird. Like, look at this. We do x1 plus x0, and then we store that into x1, right? And then we do move, like, the return value, this a plus b, is actually in x1. And now here we want to return that value, so we have to copy the value x1 into x0, and then we return it. And this kind of annoys me. Let's do something. We're going to do something which is going to be silly, and then you'll be like, here's another problem with Aaron's register allocator. So let's do this. We'll say, like, let's add a, we're going to reverse these. Let's add a and b. Let's do that. Right? So we'll do a plus b instead of b plus a, we'll do a plus b and return it. And if we run this, now it's only 2 instructions because we did x0, x1, and the resulting value is in x0. So the result of this add ends up here, and we know that when we do a return, like it's just going to return x0, so we're all good. We don't need to do that. So let me put it back. Let me put it back, rerun this, and you can see the difference. So like it results in the same value, but one fewer instruction, right? So there's another place, like we could probably do this better in the IR, or we might write a peephole optimizer where we see this and we swap the values around. But yeah, we can do. There's definitely some improvements we can make here, but that's interesting, I think. All right. With 4 minutes left, we're not going to get much done here. This time always goes by way faster than I anticipate. Okay, so we have 4 minutes. Okay, fine. All right. So the way we're going to do this is as I said, we have to convert this stack-based machine into a register-based machine. So the way we'll do this is we'll keep around a virtual stack. And this virtual stack will just keep track of like pushes and pops onto the stack. So we're going to process the Ruby's bytecode ourselves, and we're going to kind of like pretend that it executed. We're not going to execute it. We're just kind of like pretend that we executed it. And as we're pretending, we can figure out like, okay, well, when we do like, if we have a Ruby method that's like add 1 plus 2, if we do this, we know that we had to push 1 onto the virtual stack, and then we had to push 2, and then we popped off of it. So we can keep track of where these values need to be pushed and popped. And I think this is interesting because it kind of makes an interface between all of the different instructions. We know that, for example, the add instruction is going to require two values on the stack. It does get a little bit more complicated with like when we're pretending to execute. We can know what we need to push and pop off the stack most of the time, but there's some cases where we don't know that necessarily. But we'll pretend that we always know it for now. All right, so we're going to process the instruction sequences here. So we have all the iseqs. The iseqs are stored in a buffer, so we have to get the size of the buffer. So this is the buffer here. Here's the buffer. And then here are the size of the instructions, so that's how long the buffer is. Now, unfortunately, instruction sequences, like in YARV, Ruby's instructions are variable length. So we have to actually figure out how wide they are, and that's this here. So we say, like, we'll start off with our position of 0. Our position is we're going to iterate until we hit a particular size, which is the number of instructions in our system, and we're just going to add the length to that. So we always increment by this. So this length here changes depending on what instruction we're processing. So the thing we're going to JIT compile is just this method down here, foo. Foo is going to take a parameter and it's going to return the parameter. So this is very, very simple. Like if we were to look at the instruction sequences out of this dump, is this right? Yeah, let's make this a little bit wider. So we're going to dump the iseqs for this thing. So it's the same thing we had in the test script. We do foo x, return x. If we run this thing, you'll see it's only got 2 instructions. Get local WC0, too legit to quit. Which I always read WC as water closet, but that's not what it is. It stands for wildcard, and I have put that into the glossary, so please check it. What it means is we're fetching a local at position at depth 0 and at a wildcard position. So we're saying x at 0, and then we're going to return from the function. And I gotta stop here in a minute. But let me kind of explain this wildcard thing here because it might be pertinent to people's lives. Every time we create a new stack frame, like we create a new environment. So for example, let's say we had a block here. Let's say we're doing like x comma ARY. Let's say we got an array and we're iterating over the array. Do, I don't know, v, and then we're just gonna say like puts x plus v, right? When this function is called, when foo is called, these two values, these parameters, are going to be considered locals. And the instructions here, like we have another local here, this v, but this v is a local for this block, right? Now this x here is also a local, but it's a local for the outer scope. So the way the virtual machine deals with that is we have this get local instruction, and one of these, this wildcard, or not the wildcard one, this 0 is telling us how many environments backwards we need to go. How many environments up do we need to go to find this local? So when we're just getting the one value here, we go up 0. We go up to 0 environments, which is why we're at 0 here. And x happens to be the first value in that environment. Like if we did foo x comma y, and we do like x plus y, for example, you'll see here, let me pull this up a little bit. You'll see here like, oh, okay, well, y is at position 1. So we have, we go up 0 environments and position 0 and position 1. So let's say we have that block example. We'll do like y.each and then say puts x. Like this. Now we have, you see here, now we've got a water closet 1, right? We're going up 1 environment and fetching the local at position 0. And so on and so forth. We can have even more than these. Like we could have, of course, you can have many, many nested blocks in here, right? We could even do like y.each again. So now it's got to go up 2 environments. And if we run that, you'll see like the instruction actually changes. We say, hey, it's just a normal get local instruction now. We need to go up 2 environments, and then we fetch the local at 0 there. So that's why we have those. That's why there are 2 different indices for a get local instruction. We have one, which is how many environments we need to go, and then another index, which is actually get the local at that environment. Let's just run this real quick, and then I gotta go. So we're going to iterate over all of the get the instruction that we're JIT compiling, figure out what its parameters are, whether it's an lindext, like some kind of integer, and then we're going to call a compiler, like we're going to call a handler for that particular instruction. So we have, right now, our example only supports get local wc0 and then leave, and we're just going to break. We're going to do a break on leave, so this is just going to break. So here we'll say, hey, I'd like you to load the EP, our environment pointer. Remember, the environment pointer is where locals are stored, and we know that it's going to be at this particular index. We know it was index, in our case, like the code we were looking at, it's index 0, but that 0 is a parameter, and it's actually a negative offset from the value. So we'll say like, hey, it's going to be negative index multiplied by 8 because we're dealing with 64-bit integers on here, or this is a 64-bit platform, so we've got 8 bytes that we need to walk. Like each slot is going to be that wide. Then we're just going to store it into our stack pointer, and our stack, we're gonna say like, hey, we store it in the stack pointer at this particular depth. So whatever our virtual stack is at, that's where we're going to store it. And then we ask our virtual stack here to push a value. And if we look at the virtual stack, all push is doing is just incrementing our stack depth. So we push and we pop. So let's try running this. And I feel a little bit rushed here, so I know this explanation isn't perfect. Like maybe we'll look at TenderJIT more in the future, hopefully. So let's do LLDB on mjit enable. So what we're hoping will happen is that we'll get to the leave instruction, our JIT compiled leave instruction, and that'll just break. So let's see if we can actually do that. No. Yes, it is because I did this. Sorry. Let's run it again. All right, it worked. Yes. So here, let's read the machine code output. I have it disassemble the machine code before, like right here, we write the buffer out to the JIT, or we write out the JIT buffer, and then it disassembles the buffer. So that's the text that you see right here. And then we return the pointer to it. So you can see this is our, like, let's scroll up a little bit. Right here, we're fetching the EC, just like that. Is that right? No, that's not true at all. This is the SP, right? Okay, sorry. So we know that the CFP is in reg x1. So we say, hey, I would like the SP. And it goes ahead and loads the SP here into a temporary register x10. And then it stores the SP into x2. So this is kind of our like prelude here. Here's our two writes for the prelude. So we've got a load and then a load and then a copy. So we'll say here's our load and copy, load, copy. Then finally down here we get to the actual like meat of our JIT compiled code. Here we're going to fetch our local, which is a load, and it's going to be minus x8 ox18, which I guess is the index. So this is our load. So we load it from the local table, and then here we store it into the stack pointer. So right here we're doing a store. So we load the value and then go ahead and store it. And if this is working correctly, it means that the Ruby value that we passed into foo is going to be inside the x10 register. So if we check that, we're looking for the value 1. So let's print out the value inside the x10 register. Let's do px $x10. And this is correct. I'm not going to, I'm very late. I actually got to go. MRI or CRuby uses what's called tagged pointers. So 1 in CRuby is actually 1 shifted left by 1, and then the bottom bit has a 1 on it. So this is completely expected. If we use RP, which is like Ruby print on x10, we'll see it's the value 1. So that's correct. Let's do one more test here. Let's put in, just to show that I'm not like doing any tricks here, we'll change that to like 10. And we'll try running it again. You run, print out our value. Oh, that's funny. It JIT compiled earlier than I thought. Let's change it here, this one to 10. Delete that. Okay. Oh, it exited. Okay, maybe it didn't. Let's do 1 here. Let's try this. It didn't jump into my code. Okay, great. So the third, it seems like right here we execute once, here we JIT compile, but we don't call it, and then it seems like here we actually call the JIT compiled code. So if we do an RP on $x10, we should get 10 out of that. Yep, there's our value 10 there. So now all our job, the only thing that's left now is we just have to implement all of the instructions and then call it a day. We're all done. All right, I'm gonna stop here. Hopefully next month we'll probably do some profiling. Maybe we'll look at TenderJIT more, or if there's any stuff that anybody wants to take a look at. I had a really good time doing this, and remember, if you have any questions about like some of these terms, I know they can be kind of confusing, please feel free to write an issue on the Ruby, that repo I said earlier. I'm getting tired. I can't remember what I said. So please check that out. Thank you all for coming, and I'll see you later. Bye.